Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to have the lecture of 12th module, first lecture, that is 56th lecture of this course. This module basically involves the stability theory, how matrices could be useful in real life applications by using the partial differential equations, ordinary differential equations, artificial intelligence, machine learning and other approaches. We would see the stability theory. As we know, stability theory is very important, and whether the system becomes stable or whether the system becomes unstable, and if at all the system is stable, what are the conditions under which the system becomes stable. A problem of great importance is that of determining the behavior of a physical system in the neighborhood of an equilibrium state. If the system returns to this state after being subjected to small disturbances, it is called a stable system. Otherwise, it is called unstable system. A problem of great importance is that determining the behavior of a physical system in the neighborhood of an equilibrium state. If the system returns to this state after being subjected to a small disturbances, it is called a stable, otherwise it is called unstable. Although physical systems can often be tested for this property, in many cases this experimental procedure is both too expensive and too time consuming. Consequently, when designing a system, we would like to have mathematical criteria for stability being available. A linear equation of the form, that is dx by dt, will be equivalent to ax, x of 0 is equal to c, can often be used to study the behavior of a system in the vicinity of an equilibrium position, which in this case is x is equal to 0. Consequently, we shall begin by determining a necessary and sufficient condition that the solution 1 approaches to 0 as t tends to infinity. Dx by dt is equal to ax and x0 is equal to 0, and when t tends to infinity, it will approach us to 0. The actual economic, engineering or physical problem is, however, more complicated, since the equation describing the process is not as said in the equation 1, but nonlinear of the form, that is dy by dt is equal to ay plus g of y and y of 0 is equal to 0, or in general a constant. We can write this in terms of the theorem: a necessary and sufficient condition that the solution of the system, that is dx by dt, will be equivalent to ax x0 is equal to some constant. Here A is the matrix. A is a matrix. Regardless of the value of C approaches 0 as t approaches to infinity is that all the characteristics roots of A have negative real roots. So that means when you write this, dx by dt will be equivalent to A of x, x of 0 is equal to constant C. The proof is very simple. If A has distinct characteristic roots, then the representation E of A of t will be equivalent to t times of the matrix e power lambda 1 t 0 0 0 0 0 e power lambda 2 t 0 0 0 0 e power lambda n of t establishes the result. We cannot make an immediate appeal to continuity to obtain the result for general matrices, but we can proceed with the following way. So that means e power at is equal to t times of, so this is the matrix e power lambda 1 t, lambda 2 t, lambda 10 t, and these are all zeros, these are all zeros, these are all zeros, these are all zeros. In place of reducing A to a diagonal form, let us transform it to triangular form by means of a similarity transformation. T inverse AT is equal to T B. That is T inverse A of T is equal to B. The system of equations 3 takes the form dz by dt is equal to B times of Z and Z of 0 is equal to C prime, where B is a triangular matrix. Upon the substitution, x is equal to T of Z. X is equal to T of Z. Written out in terms of the components, we have dz1 by dt will be equivalent to b11 z1 plus b12 z2 etc. b1n zn. z1 of 0 is equal to 0. dz2 by dt will be equivalent to plus b22 z2 etc. plus b2n zn. z2 of 0 is equal to c2 prime. So like that you will have d of zn upon dt will be equivalent to etc. plus bnn zn. zn of 0 is equal to cn prime. Since the bn are the characteristic roots of A, we have by assumption real part of b1 1 bii is less than 0 for I is equal to 1 to n. Solving for zn, so zn is equal to c prime n e power b n n t. We see that zn tends to 0 as t tends to infinity. If vt is approaches to 0 as t tends to infinity, then ut as determined by du by dt will be equivalent to b1u plus v of t, u of 0 is equal to a1. Approaches 0 as t tends to infinity provide that real part of b1 is less than 0. And all of you knowing very well, when you talk about the matrix stability, the first and foremost thing which comes to our mind is method of Lyapunov stability. Let us now consider how we can use quadratic forms to discuss questions of asymptotic behavior of the solution of H near differential equations. This method was devised by Lyapunov and is of great importance in the modern study of the stability of solutions of nonlinear functional equations of all types. This is one of the first and foremost theory, the method of Lipnow's, for solving the differential equations. Consider the equation dx by dt is equal to ax, comma, x of 0 is equal to c. Dx by dt is equal to a of x and x of 0 is equal to c, where c and a are taken to be real and the quadratic form is u is equal to x comma yx, that is u is equal to x comma y of x, where c and a are taken to be real and the quadratic form, that is u is equal to x comma y of x. This is the quadratic form. Now we would like to see what is the form of y, how it influences the system. Where y is a symmetric constant matrix as spoken, and it is yet to be determined. That is du by dt will be equivalent to x prime yx plus x times of yx prime, and this can be written as ax comma yx plus x comma y of ax. So that can be written as x comma a prime of y plus y of a multiplied with x. So essentially you get the determined y, that means a prime y plus y of a is equal to minus 1. With the further condition that y to be positive definite, then the relation 4 becomes this equation, that is du by dt will be equivalent to minus of x comma x. So which would be yielding du by dt is less than or equal to minus 1 by lambda n times of u, where lambda n is the largest characteristic root of y. From equation 6 we have u is less than or equal to u of 0 e times minus 1 over lambda n. Hence u tends to 0 as t tends to infinity. It follows from the positive definite property of y that each component of x must approach 0 as t tends to infinity, that is t tends to infinity. However, if A is stable matrix, we can determine the symmetric matrix capital Y uniquely from 5. So Y has the representation integral 0 to infinity e power A transpose T1 e power A times of T1 times of dt1, and this property is x times of y of x will be equivalent to integral 0 to infinity x times of a e power a prime of t1 e power a t1 of x multiplied with dt1. So that will be equivalent to integral 0 to infinity e power a t1 x e power a t1 x d of t1. mean square deviation, suppose that A is a stability matrix and we wish to calculate this J, that is J is equal to integral 0 to infinity x times of b of x dt. It is interesting to note that J can be calculated as a rational function of the elements of A without the necessity of solving the linear differential equations of x. J can be calculated as a rational function of the elements. In particular, it is not necessary to calculate the characteristic roots of A. So we will have x bx, that will be equivalent to d by dt of x y of x. So this is the inner product, and we can determine this matrix Y such that this would happen. That's how you do get the stability of this matrix. Then we see that B is equal to A prime times of Y plus Y of A. So what is this value of J? J is nothing but the constant C Y of C. Since the matrix A is stability matrix, it will have a unique solution which can be performed using the determinants. So since it is a unique solution which you can able to perform, the immediate question you can ask is how it is effective test for stability. The problem of determining when a given matrix is a stable matrix is a formidable one, and at present time there is no simple solution. What complicates the problem is that we are not so much interested in resolving the problem for a particular matrix as we are deriving conditions which enable us to state when various members of class A matrices are stable matrices. So this is a stable matrix, that is A of mu. Questions of this type arise constantly in the design of control mechanism. Questions of this type arise constantly in the design of control mechanism. In the field of mathematical economics and in the study of computational algorithms, once the characteristic polynomial of A has been calculated, there are a variety of criterion which can be applied to determine whether or not all the roots have negative real parts. Perhaps the most useful of these are the criteria for Hurwitz. Consider the equation that is lambda I minus A will be equivalent to lambda power n plus A1 times of lambda power n minus 1 etc. plus An is equal to 0. Any necessary and sufficient condition that all the roots of equation 8 have negative real parts is that sequence of determinants, that is h is equal to A1, h2 is equal to determinant of A1 1, A3 A2, and h3 is equal to A1 1 0, A3 A2 A1, A5 A4 A3. And differential equations and characteristic values. You consider the differential equation Ax double prime plus 2bx prime plus cx is equal to 0. X of 0 is equal to c1, x prime of 0 is equal to c2. If we consider such an equation from the study of electrical circuits, this is a quite common come across in electrical circuits where A is a matrix, B is a matrix, C is a matrix, X prime is the double derivative with respect to independent variable, and X prime is the derivative with respect to independent variable, X is the variable, and A, B, C are the matrices, and C1, C2 are the constants. So this kind of application quite often you come across in circuit processing, capacitance, inductance and resistance, and ABC are non-negative definite matrices. On these grounds, it is intuitively clear that the following results holds. If A, B and C are non-negative definite matrices and A and C are positive definite, then this determinant happens to be 0. That is, lambda square A plus 2 lambda B plus C will be happen to be 0. Where A, B, C are matrices, C lambda is the scalar. If A and C are non-negative definite and B is a positive definite, then the only root which 0 real part is lambda is equal to 0. The proof is, let us give a proof which makes use of the physical background of the statement. In this case, we shall use energy considerations. Starting with 9, let us write x prime ax double prime plus 2 times of x prime bx prime plus x prime cx is equal to 0. Then this is valid for any s greater than 0, and which you can write it as integral of 0 to s x prime of ax plus 2 times of x prime of bx prime plus c times of, that is cx comma x prime, whole thing dt is equal to 0. So this can be written in this form. This is equivalent to the equation x prime of s ax prime of s plus 4 times of 0 to s x prime bx prime dt plus x of s cx of s will be equal to c3, where c is equal to c3 is equal to c2 ac2 plus c1 cc1. If lambda is a root of equation 10, then 9 equation has a solution of the form e power lambda t. If lambda is real and c is real, if lambda is complex, then our lambda will be equivalent to r1 plus I times of r2. Then the real part of e power lambda t, which has the form of e power r1t times of a1 cos r2t plus a2 sin r2t is a solution. So you do get the equation of this form: e power r1s b1 comma ab1 plus 4 times of 0 to s e power 2 r1t b2t comma b db2t dt, which will be equivalent to c3, where b1 b3 are constants across the vectors and b2 is a variable vector given by the equation, that is a1 r1 plus a2 r2 will be equivalent to cos of r2t plus a2 r1 minus a1 r2 times of sin of r2t. If a and c are if a or c is positive definite, then b is greater than or equal to 0. We see that r1 greater than 0 leads to a contradiction as s tends to infinity. If a comma c, that is matrices a comma c greater than or equal to 0, then b is positive definite requires that r1 is less than or equal to 0. So furthermore, since a1 cos 2t plus a2 sin 2t is periodic, we see that the integral form of this is the diverges. We have presented this argument in some detail since it can be extended to treat similar questions for which coefficients A, B, C are available. So you are getting the coefficient matrix A, comma B, comma C. So that's how you do get the different variables. So this example demonstrates how actually the differential equations of the matrices could be applied for a particular application to electrical engineering, and how the matrices, the stability could be computed, which we called as a Lebesgue stability, in order to find out the stable solutions to these matrices. So thank you very much for listening to my lecture, and the next lecture also we will do some more examples how the matrices could come across in the real life systems. Thank you once again.